Hi everyone, welcome to another one of the ZX seminars. Today we will have Simon Burton, who will be speaking about genons, double covers, and fault-tolerant Clifford gates. Please, Simon, take it away.
Thanks a lot, John, and thanks for inviting me here. Invite people to interrupt with questions, especially if you see me drowning. Your questions can help to bring me back into focus. So what I'm talking about today, there's really three aspects to this stuff. And between stabilizer codes, manifolds, two-dimensional manifolds, and ZX calculus. I won't be doing a lot of ZX today, but I'll try to patch in why this is so useful for this work and a really great way to think about this stuff. And there's a kind of a triangle here. The connection here would be called, I guess you would call these topological codes. Like the surface code. Toric code, etc., etc. And the connection here is that we often use circuits with our codes, encoding circuits, transcoding circuits, or endo circuits, which would be gates applied to our codes. And I guess I'm still really curious about this connection here, and I feel like the other shoe hasn't dropped quite yet. There's a lot of interesting stuff connecting, say, algebraic topology and ZX calculus. So let me start off talking about the ZX. And I wouldn't say I'm an expert in this stuff, but I really like it. So what am I trying to say here? Okay, so so it's something like a lot of the time when I'm working on stabilizer codes, I'm really just thinking about symplectic spaces. And with these things, the S gate the S gate is really squares to the identity. And so another way of thinking about this is we want to think about Clifford gates, but modular. I mean, a lot of people, when they talk about Cliffords, they talk about Clifford's modulo phases. But when I think about Cliffords, I think about Clifford's modulo phases and the Pauli's. And this gets you to, I guess, these symplectic spaces. And here the key is that pretty much this is, so normally S squared would be what the Z Pauli, but if we're modding out by the Pauli gates and the phases, we have this equation. And as a symplectic matrix, this S gate is going to, I'm going to write this S as just a matrix, 2 by 2 matrix. So this is acting on a small symplectic space. And this, let me organize my windows here. This process which I'm describing here is going to take one of these symplectic ZX calculus. Well, it's really, what else do people call this? Symplectic ZX. It really shows up in this work here. So I think Robert was talking about this at the ZX seminar in February. This is, I think they call this the graphical symplectic algebra. So that's what I'm talking about here as well. And this, so what I'm describing here is a process, and I'm never quite sure which way this arrow is going to go, but right now it's going up. And what I'm going to do is take this S gate and write it as a phase-free ZX diagram. And it's going to be, let me see if I can get this right. So I've got a bunch of weird conventions here. So first of all, I should say I'm not using the usual ZX colors. So I've got my Z is going to be green today and my X is going to be blue. So I hope that doesn't result in immediate banning from the ZX community. And the other weird convention that I have is that my diagrams are going right to left here. I'll try to draw these arrows to remind us of this. So what this picture is a picture of the tangograph of this S matrix down here. But if we interpret it as a ZX diagram, it's a C0 between the two qubits. So what we're doing is we're starting with this, what I'm calling stabilizer ZX calculus. Was probably better to think of it as graphical symplectic algebra, and then applying this doubling or unwrapping I'm never quite sure what to call this, to get a phase-free ZX calculus diagram, and that it has a symmetry. So you don't hit any phase-free ZX calculus diagram. You only get these symmetric ones. So now, all right, let me just mention, right, I should mention this other reference here from 2017. They use this map to prove a theorem in their paper. They use this as a semantics for the ZX calculus to show a result in this paper. Is that a question? Okay. So now let me say the same story, but from the point of view of stabilizer codes or symplectic vector spaces. So if I have a vector space, a finite dimensional vector space, my pen is so thick, vector space V, and then I take the direct sum with its dual. This thing is naturally a symplectic space. You use the pairing of a vector with its covector to turn this into a symplectic space. And then if I actually start off with a symplectic space and a code, which is just a subspace, this also still applies. And I get a code. Let me just write it as the double of the code. Sits inside this doubled thing up here. So what's happening is we can take any stabilizer code framed as a symplectic subspace or an isotropic subspace of a symplectic space. Yes, this is isotropic. And then double it, it just functorially gets carried along with this. You get a CSS code also with a symmetry. And this construction was first written about by Kovalyev and Priedko in 2013. And the important thing about this is that if we have distance d down here, then the distance is at least d up here. So after we've unwrapped the code, the distance is preserved. And this was also used in this other work in 2023, where they applied it to subsystem codes. And an important part of what I'm talking about today is that this is a functor. This is functorial. So if you have a Clifford gate, and I guess when I say Clifford, I mean Clifford modulo polys and phases, that the Clifford gate will lift to a Clifford gate up here. So that's really an important part of this whole story. And also that the symmetry also gives you further operations on your codes. Question?
I think there was just some background noise, if you want to continue.
Okay. So let me give an example of what I just described. And so down here, I'm starting off with a stabilizer code. It's a 412 stabilizer code. So four qubits, one encoded qubit here and distance 2. And these are the stabilizers. I use a dot for an I. So it's X, Y, Z, I. I hope everyone is comfortable with this notation. And I'm omitting the tensor products as well. Whoops. So there's 3 stabilizers here. So it's encoding 1 qubit. And here, this is the symplectic. I'm writing this as a symplectic matrix. So the rows of this matrix span an isotropic subspace, which is my code. And what's going on here, if I just show this by example, I'm going to, how does this work? So you'll see there's a copy upstairs. This thing got copied. And then this one, it has the 2 pieces swapped around. Now, in terms of the Pauli operators, so right away we notice this is a CSS code, as I claimed, and it has a symmetry. So if I swap the first 4 and the last 4 qubits, my x's change into z's. and the same with these other guys. So it's a CSS code with a symmetry, and I think elsewhere this is called a ZX duality. Oops. It's a way of swapping the qubits around that exchanges the Z and the X operators. So the topological story, this is pending my, I really need to, I get better at doing algebraic topology. But the idea here is that we have a compact two-dimensional manifold. So these are, maybe I should also say oriented. Hope that's all the adjectives I need. Maybe I should also say closed because there's no boundary. And this decoration is, it's going to be called a domain wall. So that's a physics terminology. And I'm going to do this as an orange colored thing. And the idea is that this unwrapping is, you know what, I'm going to just swap down to one dimension over here because it's much easier. So let me do the one-dimensional story. So we have a compact, closed, oriented, one-dimensional manifold. Luckily, these are just circles, maybe many copies of circles, so that's easy to draw. And then the double cover of a circle is going to just be like this, two circles. And when I start drawing these covers, I keep wanting to draw the arrow in the other direction. And think of a point down in the base space is double covered by 2 points up here. So we call this the base space. And this is the cover. And the decoration or the domain wall in one dimension, this is, domain walls are just going to be 0-dimensional. Let me do this in orange. If I put a 0-dimensional domain wall, double cover is going to be, well, there's a recipe here. So that the domain wall is going to swap the two sheets of the double cover. So I end up with this. It's just a single circle wrapping twice around the base space. And later on, I'll do this. I'll draw these same pictures in 2 dimensions. And the domain wall will be a 2-dimensional line. And then we'll be cutting and sewing the cover according to the domain walls.
Simon, maybe you misunderstood. Is the domain wall in this case the dot you drew on the circle?
Yeah, it's this orange domain wall. It's this orange dot, yeah.
And are you now saying that there's different types of covers for the same base space? That kind of thing?
Yeah, so the base space is this compact 2-dimensional manifold with a decoration, which is this domain wall stuff. Yeah.
Okay.
So what does the domain wall, maybe you'll explain this later, but what does that have to do with this crossing here? I don't see how those bits of data are related to each other.
Yeah, so that, yeah, this is important to, I'll have a few goes at explaining this. So every time on the base space, when you cross over the domain wall, in the covering space, you have to swap the sheets. So this arrow in the base space, maybe I can draw a different color here. So let me try yellow. So if I have this, does that even show up? No. Let me try purple. So this purple arrow in the base space would lift to a purple arrow that swaps sheets.
Okay, so somehow I'm distinguishing being in the top sheet versus the bottom sheet of this top object, and then crossing the main wall is when I'm moving between these two different places in the covering space.
Right. Maybe another way of drawing this would be these would be some kind of portal in the covering space. So that when I cross into the portal, I come out the other one. But really, topologically, that is what I just drew before. There's another hand.
Yeah. I wondered if this is meant to be more than just a description of an artifact that arises from the choice of representation, but given that you're using the representation in artifact, that's sort of important to note. Or is there something more essential than a negotiation with the representation going on?
There's so many ways of formalizing this, and I don't know if I've really settled on a slick formalism yet, especially since my algebraic topology is so meager. Yeah, maybe I'll just try to forge on, and we can all of us negotiate something. And so I should also add here, there is going to be a symmetry here as well. It's the thing that swaps the sheets is the symmetry. Over here, it's really obvious what the symmetry is, but here it's a bit more tricky because the sheets are intertwined. But yeah. So I'm going to switch to, now I want to combine all these things together and talk about topological codes with domain walls. And I'm phrasing this in a way that when I talk to people that don't know a lot about stabilizer codes, that I can still explain it to them. And the idea here is we have these two maps. These are two examples of maps, and the red things are going to end up being the qubits, the red dots. And the idea of the map coloring game is to take each of these tiles and color them either green or blue. And I think it's not too hard to see the kind of coloring we're going to need. It's just a checkerboard. So I'm doing this right. Yep. And I like talking about it this way and thinking about these topological codes using these colors, because I guess I just like drawing pictures. But what happens is the green is going to become an X type stabilizer, and the blue is going to become a Z type. I totally got that around. Blue is X. All right. It's because I'm talking to ZX people and they don't know what colors I'm using. All right. And so we get these two surface codes by playing the map coloring game, this 913 surface code and a 25 qubit surface code. Okay, great. Now, this is well known when you take a CSS code. If you take any CSS code and you have two copies of it, you can apply a CNOT gate between the two copies, between the qubits, every qubit of the two copies. So it's going to be like this, and so on and so on. So I get, what is this, 9 C0s. This is a transversal gate that acts between the two codes. And what's maybe more relevant is that if I swap the stabilizers on one of the sheets, then the transversal gate just becomes a CZ between. So this is 9 control Zs. And watch out, my arrows have changed direction when I'm drawing these double covers. So I think I already explained this. In general, what I'm going to be doing is having some topological two-dimensional manifold and drawing some map on it. And it's going to be a 4-valent map. So at every vertex, there are 4 edges. And then I'm going to be playing this map coloring game. And as long as my colors don't disagree across a vertex like this, I get a stabilizer code. So this is ruled out because these two faces won't commute. So this is my map coloring game. And I want to do this on some nice surfaces. So here is an example of the map coloring game on a torus. And I have 16 qubits. And if you do all the counting, you work out that there are 2 encoded qubits, and it's the logical operators are distance 4 at least. You could think of this as either map coloring or stabilizer codes. So if you don't know anything about stabilizer codes, you can just think, oh, we're coloring in maps here. This is another example, this time with 8 qubits, and it's kind of spiraling around the torus like that. And this one is a slightly more skewed version with 10 qubits, slightly different spiral. As long as the boundary conditions, you can see this blue square matching up with this blue square over here.
Simon, can you remind me what the logicals are again in this picture?
Ooh. So we're
If that's
expecting
easy to say.
It's going to be something like this. Yeah. And I guess so how is this going to work? I guess is this going
If
to
you
work?
want to do this with the easier picture, that's also fine. If you want to go back to the square lattices here.
Well, let's see, does this even work? What if I just put X's here? I mean, the point is that the logical operators wind around the torus. And there's 2 ways for these things to wind around. And that's why we get 2 qubits.
And so is it self-dual?
It's not self-dual because that's a good question. So this is a X-type stabilizer. So if we swap this with a Z, we would get a different code. But you're kind of pointing out that if we swap the colors and then translate the lattice by 1 unit, we would get back to where we started from. So this secretly does have this ZX duality. It's a way of moving the qubits around that swaps the colors.
So can I think of the logical Z and X of a single qubit as being 2 parallel lines? And then sort of orthogonal lines are like the different qubits?
I think the orthogonals are the same cubic because you want these to anti-commute. So you would have, I hope I'm doing this right. So that would be a Z, Z, Z. So this one would anti-commute with the X.
Yeah, I
Hmm.
think you have a pair of qubits, right? One
I'm not
like
sure
as
how this
you've
works.
shown, and then the other one is I just reversed the Z and the X.
Okay, that also
logicals.
works.
Yeah.
Maybe it's the same as what I just said. Okay.
So there's two qubits in there, unlike surface code, which only has one.
Oh, and then so like a transversal Hadamard switches between the two qubits.
Transversal Hadamard, but you need to move the qubits. You need to translate the lattice. Yeah.
Mm.
Yeah. So that's what this ZX duality is. Yeah.
Right. Thanks. Sorry for derailing.
I guess please derail. I love it. So I guess a ZX circuit would be like this, something like this. You do that across the ZX duality. Swap the two guys and Hadamard. Yeah. And yeah, I do develop a theory of string operators, which I've totally forgotten, which tries to explain how the logical operators work, which I just screwed up, but it's not too complicated. So now I'm going to start to change the rules of my game, because sometimes these so this is an example where the map coloring game just fails, right? There's going to be two blues next to each other. So how do I fix this? So I'm going to have a blue, blue, green, and then, so what I'm going to do is insert one of these domain walls. So it's kind of an artificial extra bit of decoration that allows me to write a stabilizer as half a ZZ and half XX. So that's what I've drawn here, and that's the boundary where my colors are changing is the domain wall. And this is still going to be a valid stabilizer code. If you look locally, say between these two stabilizers, these two adjacent stabilizers still commute. So I'm expanded my rules of the game, the map coloring game. Right, that's what I've just been drawing. And now the double cover, this is a two-dimensional picture of the circle picture that I was drawing before. I think before I just had a circle with a one-dimensional domain wall, and that's actually this edge here. I've got a torus here, and that's a circle going around the torus with a zero-dimensional domain wall. And these are the two sheets, and you see that one of the sheets has the colors reversed. And it's a good thing that I practiced this in one lower dimension. So when I'm moving across the base space here in the double cover, I'm going to go through the portal and end up here. So this covering space, I'm really cutting along the dashed line and re-gluing the space. something like that. So this is the space upstairs is just it's still a torus, it's just twice as long as this torus. So this is, what is this, 12 qubits down here, and up here it's 24. Am I doing that right? So this is still a toric code. It's going to be a 24 to, and I think the distance is, oh, the distance down here is 3. Oops. I think the distance upstairs is bigger now. It's got slightly bigger.
And Simon, just to check, with this double cover, one of them gets their colors flipped when it's mapped to the base. Is that correct? The top
Yeah.
one gets colors flipped.
Yeah. It's to do with this. When I was talking about taking a vector space and turning it into a symplectic space, one of them is dualized.
Right.
And this is a more complicated example. We've got 2 domain walls now, so it's going to be, we're going to have to swap the sheets in both directions here. And you could just look at, it's right. So the other thing I didn't point out, so in this previous example, this guy upstairs is a CSS code, because this green patch here is connected to this other green patch there. So it's just one green patch. So the colors in the covering space are not, they're single colored tiles. So it really is a CSS code. And the next example is just, you could look at these 2 green patches here are connected to these 2 green patches down here. So this is still a CSS code. Cole.
In this example, is the total space still a torus, or is it some weird?
Yeah, it's still a torus.
Okay.
Yeah. And what is this? I've got 9 qubits down here, so I think this is an 18. I'm not sure. Did the distance, it really looks like the distance has increased. I'm not totally sure. Well, I'm not even sure what the distance downstairs is. I think it's distance 3. I'm not totally sure. It can be tricky working that out. So yeah, it turns out with these codes, they inherit. So the ZX duality gets this CZ Clifford gate. It's a transversal CZ. So this is going to be the 9 CZs is going to give you a transversal gate on this 18 qubit code. So I'm going to even make the map coloring game even more complicated now. So up here, I think my colors are good. And going vertically, it's fine as well. It's just the transition over here, which it seems like we need 2 colors on these tiles. So there's a domain wall, chopping these stabilizers in half. It's still one stabilizer. that's like what we saw before. But here, you'll notice also there's a 3-valent vertex. Here and here. So the 3-valent vertices, that's where domain walls terminate. And in this paper, I've been calling these genons. There's actually some references that I forgot to include, but this is Barkeshley. Oops. And these are also called twists in the literature. And the other reference here would be Bombin. He was originally, I'm going to say, 2012, something like that. But it was Barkeshley that came up with this idea that you can unwrap these spaces and think of these, the endpoints of these domain walls or twists. You can think of them as these unwrappings. And so these twists, which behave sort of like particles, have to do with genus. So that's the etymology of this term, genon. All right, so that's what I'm doing. Actually, there's a slight wrinkle here is that I'm going to draw these little half edges here and pull the genon slightly off the qubit. All right, so this is how the map coloring game is evolving. It's my game, so I get to change the rules. And the double covering around the genons, the basic idea is that downstairs, when you go once around a genon, upstairs, it's not enough. You end up on the other sheet, so you have to go around twice. I'm not expecting anyone to understand this picture right now. But you'll notice there's a little half edge in the base, which gets turned into a full edge upstairs. And this is important because the map coloring game in the covering space, we want it to be a CSS map coloring game. So that's an important part of the construction.
Simon,
Yeah.
when you draw these or give these examples of like when I do this with the path and the base, then this happens upstairs. Are you thinking about like path liftings like you would have for a fiber bundle? Where
Yeah,
I sort of
exactly. Yeah.
So I give you a point in the total space, I guess, and then I give you a path in the base space, and you're just saying what path is that upstairs? Is that the point?
Right. So that's a good way of explaining it. It's something like that, I guess.
So the point is I kind of need to know which sheet upstairs I started on to figure out what the path is.
Yep.
Okay, cool.
Thanks for that. 15. So this was a small, interesting example that we came up with. And it's got 4 qubits. And these are all trivalent vertices. So I'm expecting to see 4 genons. And it's kind of arbitrary how you connect these with domain walls. And I guess what I'm going to be saying is that these always come in. There's always an even number of these genons. If you fool around with Euler characteristic and so forth. Well, I kind of skipped an important thing, which is this is on a sphere. I'm thinking of this on a sphere. So this gray area wraps around behind. Now that I've drawn the domain walls, I can fill in this with blue and green, which I think I do that on the next slide. And put in my stabilizers. So I guess there's another thing that I forgot to say, which is the little point where the genons are. Is that here? Yep. So where the genons connect to a qubit, I stick a Y. So there's kind of like an outside stabilizer, which is redundant. And the three faces there. But now the question is, how do I double cover this thing? Does anyone happen to know the answer, how this works? I'm going to just take a detour. I guess I've got about 10 minutes. So I think I can make this detour, which is a map of the Earth that C.S. Persk came up with in the 19th century. And you'll see that there's some weird stuff going on here. Like there's two copies of Australia. I've just redrawn the map with using my picture here. There's the two copies of Australia. And if you look, you'll see that that's Africa here, connecting over here. And also this is Africa, connecting onto Africa here. So actually this thing is a torus. So it's a double cover of the Earth, which is a sphere, by the torus. And it has these four weird points where if you go around this weird point, you see Australia twice. So those are going to be the genons in the base. Now drawing this, right, that's what I just said, that this map by Peirce is a torus double covering the Earth. Well, I haven't drawn the genons down in the base space. But I think I have a moment to share a little animation. So this is the torus going around, and I'm doing this rotate. The torus is rotating on a skewer that goes through the weird double genon points. And you'll see that's Australia here. And if I just rotate torus halfway, so 180-degree rotation of the torus around the skewer, I get back, here is Australia again. So you can see that this 180-degree rotation is this symmetry that the double cover manifold has. Oops. Yep. Okay. Right. And as a code, this is a 412. Getting double covered. Which way is my arrow? And the double cover has twice as many qubits, and it's a toric code. And this is, I drew this picture before, and this is actually the original stabilizer code that I drew with the stabilizers X, Y, Z, I, etc., etc. That's the flattened out picture of the 822 code. Right, and this is what happens to the functoriality of this construction, taking the vector space to its double cover. Whoops. Because maps on V lift to maps upstairs, we get this result that Clifford gates on the base code lift to Clifford gates on the double cover. And also it turns out that you get this fault tolerance property. And if I had time, maybe I'd go through some more examples. We actually did experiments on the Quantinuum hardware. So I've just talked about how the 412 code lifts to the 822 code. The 513 code, which has stabilizers. You can also think of this using the map coloring game. This is like a weird twisted toric code with a lot of domain walls. Double covered by this 1023 code, which was the example that we did with the logical operators that I didn't quite work out. All right, so my concluding slide is I need to learn some algebraic topology to really figure this stuff out.
All right. Thank you very much, Simon, for the interesting talk. I can imagine there's quite some questions. Anyone want to go first?
Yeah, I have a question. I couldn't find the hand raising button. So you drew this picture of the double cover that once I made the double cover, I could do a transversal CZ between the two layers. And I was just trying to see how that would work, because at least initially it looks like a transversal CZ between the two layers would send a logical operator to kind of like half a logical operator, or it would sort of change half the logical operator. So it's not obvious to me that it preserves the logical, that it sends logicals to logicals.
Well, we had this, it's possible I made a mistake, is one thing I'll say, but the other thing I'll say is, what about this other example? So that was
a torus, I think.
Yeah, so this was so with two copies of a CSS code, you can do the C notes. So I think we're happy with that. If one of the sheets has the colors reversed, I'm claiming that CZ is the gate. Because does this work, right? So previously it was a C naught.
Sorry? We just see the torus of the Earth still. I don't know if you're sharing the wrong window or something.
Oh.
I see the right slide.
Oh, you see the right. Okay, maybe the problem is on my side then.
I'll try resharing. Do you see the 9 CZs?
Yeah, I see this now.
Right. So we started off with 9 C knots, but then I flipped the color of one of the sheets. So that corresponds to conjugating my C knot with a Hadamard. I hope I'm doing this right.
Yeah.
Which is equal to, wait, is this one of the ways of drawing a CZ?
Yeah.
Yeah. So do you agree with this picture?
Yeah, that makes sense. But this is with the 2 disconnected copies of the code, right?
Yeah. So my doubling procedure, it always lands in a CSS code with this ZX duality. But if you start with a CSS code, you just get 2 copies of a CSS code with one of the sheets has the colors flipped. So so in this picture, that's how the CZs work. And maybe I'm going to leave it as homework to try to think of how this is still the same thing going on here, that this also should be a CZ between the fibers. The same thing works here. Even though globally this is not 2 codes anymore, locally it still looks like you have 2 sheets with one sheet the color reversed. So that's my really hand-waving justification for how the CZ works.
Yeah, I guess the thing that was confusing me about that is that the logicals have changed now, right? So now that we're not 2 disconnected copies, I don't have 2 exact copies of the logical. I would have just one logical that kind of wraps around both sheets.
Yep.
And then it seems like you're going to mess up that structure if you apply CZs between different qubits involved in the same logical operator. But maybe it works out in some kind of non-trivial way.
I'm claiming that it does, but I'm not claiming I can work it out right now.
Okay, yeah, that's fine.
Yeah.
All right. I saw that Michael Janus also asked a question of said in chat he has a question, so I just want to give him the opportunity to ask it if he wants.
Yeah, I don't have it quite nailed down right now, so I'll wait a moment first.
All right. Then Aditya, do you want to?
Yeah, it's actually
right.
Yeah. I'm a bit confused over what exactly it is that you're trying to do. I sort of understand that you start with a stabilizer code. The genons allow you to distinguish stabilizer codes from CSS codes in this notation. Is that right? And then you turn this into this double cover. And I don't understand why at that point you care about the fibration anymore. Surely at that point you just have another code and its properties.
The fibers carry these transversal gates, or what? Well, they're not transversal.
Which allow you to do Clifford logicals in the base code.
Yeah. So this one does not. Let me think about this. So if you so I guess the 513 code is a good example. And you can think of it as living on a torus. It's twisted with a lot of domain walls. I think the picture is in the paper. And this is double covered by the 1023 CSS toric code, which I did show a picture of. It's this twisted toric code thing. And the 513 has this transversal SH gate.
Yeah.
And that lifts, if you follow this recipe that I was talking about at the beginning, you treat these as symplectic gates.
Yeah.
So the S lifts to a C naught, and the
And the
H
H
just
swap.
lifts to a swap. Yeah. So now I'm claiming if you apply this 2-qubit gate on the fibers of this cover, you
Yeah.
get a transversal gate on the 1023.
Yeah. So the takeaway, so I'm still lost as to what the takeaway is. It allows you to turn stabilizer codes into CSS codes with operations all described by transversal CNOTs and swaps.
Well, I mean, there's so many takeaways. I'm not sure if we're going to be able to fit it all into one basket, but so yeah, one of the takeaways was, yeah, given any code, you can come up with a double code that preserves the distance.
Right.
Another takeaway is that while Clifford gates on the base code lift also to the double code,
Yeah.
another takeaway is all this topological stuff. So some of these codes are topological in nature, and then we can start interpreting these domain walls as part of the lifting operation.
Right.
So there's really a lot of pieces here. Yeah.
Because I guess the thing that you would like to do that we're not quite able to do yet is to study the base code from its cover.
That I'm sure it's yeah, you're right. You're probably right. This is a two-way street.
Right.
Stuff upstairs might also work downstairs. Another thing which I didn't mention is when you start taking these topological codes, you can think about Dehn twists or braiding of genons around. So those are all can be implemented with Cliffords. So so it's really, this is another interesting topological part of the stories. So braiding, these are code deformations that hopefully will land you back at the same code that you started at. Braiding these genons around lifts to Dehn twists because there's no genons in the lifted code. They're all unwrapped, but they turn into Dehn twists of these higher genus codes. So that's another thing you can study. So yeah, there's a lot of takeaways. Yeah.
Cool.
So you're working all with the symplectic stuff over finite fields, but
Yeah.
if you did the same sort of thing but over the real numbers, then would this vibration be the cotangent bundle vibration?
Yeah, yeah, right. That's a very fancy way of
But it's always this. It's always the same kind of vibration, like just the kind of cotangent type
Yeah.
one, I guess.
Yeah, the cotangent. What is it? The cotangent bundle or something?
Bundle just meaning it's a fiber bundle, like a vibration. Yeah.
Yep. Yeah, so it's a kind of a well-known construction, really. Yeah, shows up all over the place.
So, Simon, if I understand correctly, if you start with like this torus with some faults in there, and then you use this double lane construction, you still get a torus. So somehow this like two-dimensional shape remains a two-dimensional shape. Like, do you have some kind of like dimension property?
Yeah, so it's always still two-dimensional, and the key, I guess this is another part of the story which kind of was the motivation for a lot of number theory and algebraic topology, but there's a key formula which is the Riemann, don't know if I can spell their name today, but the Riemann-Hurwitz theorem, which talks about ramified covers. So this is, you take some genus G surface and you think about covers that are double covers except for a finite number of points where it's a single cover. So those are the genons. So yeah, so there's the Riemann-Hurwitz theorem, a formula that tells you the genus of the unwrapped thing in terms of the genus of the base space and the number of genons.
And do you know how this interacts with some other code constructions, like hypergraph product or something like that? Like if I take the hypergraph product of a repetition code itself, like at a surface code, like can you sort of do like if I first apply this construction to double it on two codes and then I take a hypergraph, like does that commute with like doing that first and then sort of taking the cover?
I guess, yeah, well, there's a lot of tricky stuff there. The first is that when you're using that homological language, you're already in the CSS code territory. So that would be the first thing to work out. But the other thing is the homological product is, as you say, it's higher dimensional as well. So you would quickly end up with these higher dimensional codes. But yeah, that sounds interesting, like thinking about those connections. Sure, yeah.
So I guess related to that, if you do this covering construction with a CSS code, like do you get something that's like trivially two codes? Are they sort of not connected?
That's right. You just get two copies of the original CSS code and one has been dualized.
Okay, so you really want like a non-CSS code for something interesting to happen here.
That's more interesting, yeah.
And so maybe thinking another way, like if I start with a code that has like interesting properties, like with surface codes, I can do lattice surgery. If I then sort of take this down to the base space, like does this tell me something interesting about lattice surgery? Like
well, whatever, if you want to go the other direction, and this, I guess, this links to your previous question. If you do something in the covering space that intertwines with the ZX duality, that should descend to the base space. So whatever you do, maybe even this hypergraph product stuff, if it intertwines with the ZX duality or any ZX duality, that I'm going to have to say some fine print, I guess. You need to choose a ZX duality that doesn't fix any qubits. That is a squares to the identity and doesn't fix any qubits. Then you'll find a way to wrap your code up along that ZX duality. And if your operation intertwines with that ZX duality, it should descend to the base space.
Related to my previous question, so if I start with a non-CSS code and I take the cover, I get a CSS code. So then if I take the cover again, I get something trivial, which is just two copies of the code. Yeah. Is there like some kind of deforming operation you could do so that you could continue to like get non-trivial sort of covers of covers of covers that are still sort of one big code and not just product codes like that? I'm not sure if it's something you would want to do, but
that all sounds really interesting. I think this stuff surely has to have other examples. I mean, it's a kind of a Galois theory covering space construction that I think something like this should work for color codes. So you have three colorable graphs that in the base space, they're not three colorable, but then you'll be able to lift to get a three colorable graph. So there should be, if someone wants to work this out, that would be amazing. There should be some kind of story for color codes. Yeah. And I don't know what other examples are out there, but yeah.
Nice. There's maybe a question for the audience. Has anyone ever represented a toric code using a ZX diagram, like the encoders that Alex found for the CSS codes? Like, can you sort of make a nice toric picture of in a ZX diagram?
I was actually attempting to do that right now, but I'm failing. So
yeah, because it's hard to do stuff in 3D.
I mean, can you just send the like wires on the right and like wrap them around and then
Yeah, but that's not what you want to do, right? You want to make an actual torus.
make an infinite number of copies and deal with that way.
The universal color.
Okay, do we have any more questions?
I was gonna, I'll try and ask it like this. So, when it comes to algebraic topology, there's obviously these sort of two halves of homology and cohomology, and I was sort of curious whether or not sort of cohomology had sort of entered into this story at all.
Yeah, so that's a great question. So I think the answer is yes, that you would think of green as homology and blue as cohomology. And the reason why we're able to play with them both at the same time is Poincare duality. And so if I was a real algebraic topologist, I would be able to say this properly, but there is a story involving all those that works very nicely. Maybe you can work it out for homework and tell me what you come up with. But yeah.
And kind of on, I think this is technically related, but I don't remember any of the story well enough to actually pretend that I can make it related. I know that one of the stories that you can play with, like Riemann surfaces in particular, is this idea of, let's say you have some sort of free parameter in your Riemann surface and you just deform it to get back to the original one. So maybe analytically continue it. I think that's the right way to say it. And then you end up with sort of stories of like Picard Fuchs, et cetera, has that. But it seems like for this one, everything's sort of locked down in terms of where the branch points are. So it'd be kind of hard to tell a story like that.
Are you talking about modular forms and all that stuff?
I don't think so, but it's been so long that I might be forgetting. So I have in mind something along the lines of you start off with let's say the simplest example I know is you start with elliptic curve where you have branch points at 0, 1, and at and infinity and at some parameter lambda, and then you sort of analytically continue lambda around the Riemann to get back where you start.
Yeah.
And then
So
you end up with like differential equations to describe the evolution of periods on the Riemann surface. That's my vague recollection of it.
I think what you're describing is what I would call braiding genons. So you're braiding one genon around another one. Yeah.
Okay. That makes sense.
Yeah.
Okay.
Actually, I have a bit of a noob question. So I see people use this term domain wall, and I know it comes from physics, but I actually have no idea what it means. Can you sort of explain a little bit about the intuition behind this term?
Yeah. So, okay, that's a good question too. All right. So I guess what's happening is you would have, how is this going to work? You think of in the anion picture, you have, I guess you have X type and Z type excitations or particles. And then when you cross over this domain wall, it's swapping what kind of excitation you have. So I guess that's a quantum domain wall, but a classical domain wall is more like if you have a magnet where, say, one half of the magnet, all the magnet is pointing in one direction, but then on the other side of the magnet, all the little magnetic spins are pointing in the other direction. So the domain wall is kind of separating the two ways that the spins can line up. I don't know if have you heard of Ising models? That's another good thing to think about. Or a repetition code. Does that help at all?
Yeah, so like in an Ising type thing, this would be something that emerges sort of spontaneously, right? Like this change in that's going spin up, spin down.
Yeah, so it's stable in both of these regions, but then there's I guess, how would this work? the domain
I guess you
wall.
can just think of it, there's like a certain pattern, and at some point the pattern is broken, and like at that point
Yeah.
there's like a thing, and then we call that thing a domain wall.
Yeah,
Okay. And then in practice, does this correspond to like some like energy barrier or something like that?
not necessarily. I guess it's here. It's yeah. What do you? Yeah, I mean the other thing that we haven't talked about is Hamiltonians. The Hamiltonian picture. It doesn't cost any energy for an anion to pass over the domain wall, but maybe imposing the domain wall, like especially in the case, yeah, I'm not sure. Yeah.
Can I think of it as in some systems you can speak of like frustrations, and a domain wall is like the boundary between these two areas that sort of creates a frustration. Like it's
That
just
sounds good.
it's just
Yeah.
a thing that and yeah.
Yep.
In physical context, you also have the aspect of that typically, you know, the transition between having domain walls and not having domain walls, you have some kind of phase transition going on. So, you know, the closer you are to the phase transition, the bigger the grains are, and therefore the farther apart the walls are. Whereas
It's really kind of like it's like an emergent thing. Like it's not like a foundational. It's not like a primitive object. It's not like you look at these Z's and X's and you see like this pattern change, and then like at that point you say, oh, there's a wall.
Yeah, it's a little trickier than the usual classical picture, because in the usual classical picture you like can have domains sort of grains oriented however you want, but here you'd want it just to be up or down, as it were. So it doesn't quite work out as easily.
Yeah. I guess I have to learn more physics to really appreciate this metaphor. Okay. Do we have any more questions in the audience? See, most people have already left after this lengthy discussion. All right, then Simon, thanks again for the talk and for answering the many questions.
Yeah, thanks everyone for the questions. That was really helpful.
Fine.